the particular solution chapter 4. This one is one of the examples that shows that we can use a mathematical method to solve our environmental modeling situation. But in reality, our nature is not that much simple. But we always have to keep in mind that we need to keep our common sense. And if we collect this common sense in a very systematic way, that's science, okay? And then this one can somehow develop technology, right? Okay? So we are now talking about this, okay? And somehow in our reality, there's a lot of forcing functions, impact factors. So in general, it's very difficult to solve our situation by using one simple mathematical method, but this one will give you very basic idea how to move through the problem. Okay, and I don't want to repeat the same method in here, but if we have situation like this, which is ordinary differential equation, we can have integrating factor, which is e to the power of, like this one, pt right here is there. And as you know, this one can be t or tau or x or y or whatever, as long as you have something in here. Because eventually when you solve this integration, and this will be the function of whatever in here. If you have t, then it's going to be the function of t. If you have x, and this, that is going to be the function of x. So in here we call that as dummy variable. That means that can be anything, right? So anyway, we don't really care if it's t or whatever, because it is eventually solved for anything in here. So we have this term, we multiplied that to every term in right-hand side and left-hand side. And then we know this one can be collected like this, shrink like this. And then by the definition of differentiation and integration, we can integrate those both inside like this. And since we differentiated and integrated, and by definition of the mathematical term, we can just have this term right here, like that. So even in here, what is good for us is we don't have to really solve this equation. The only thing that we have to do is apply the boundary condition. Okay. So eventually in here, this one is going to be, this will be solved somehow, and then if we apply this t and 0, and then we all know this one is going to become the function of t, right? And in here, we don't know yet, because this can be very complicated to solve, but in your last class, you practiced by applying different qt in here. And if this one is just a constant, it's going to be very easy to solve. And in here we usually have constant, which is lambda, so it's not a big deal. So just going to be the e to the power of lambda t is usually the form. And then if you have a linear function and or sinusoidal, whatever, then you can just simply solve the equation. And then by applying the boundary condition, we can have one thing and the other thing. Then eventually what you have to do is solve for CT, which is that we are looking for. Okay? So impulse loading is something like, no. Impulse loading is something like this. When you have a just concentration, you didn't have anything. And all of a sudden you have something happening here. In other words, you have some kind of material dumped into the system. And then what this one means is you start to have concentration here. You didn't have any concentration at this time, and from this time you will start to have concentration C0. That's what it means. This one is called as delta function. And this one is very often used in many different situations, especially for groundwater. In groundwater, sometimes you have water, no water, because that's a mixture of soil and water inside. So delta function is very often used there. So in here, that means W in here, you can regard this as 0. In this case, only thing to say is this one has started to have C0 from some time. And if we define that as Ti equals 0, then it's very easy. Because we have a C0, no input, and then that means you have just 0. So it's, in reality, it's very easy. You can just assume this as 0. And this one means that this one, okay, this one start to have some concentration from some time. In this case, for simplicity, I just assumed my T as 0. But this T can be anywhere. But you just have to move your axis to here and then start from here. So it's not a big deal. Okay? And then the second one is you start to have loading from some time, and then keep having, you have a loading that keeps discharging to your system. It is continuous. So this one is like you start to have a factory or wastewater treatment plant. From some time they start to operate and then going on and on and on all the time. And their discharge is almost constant. In that case, we have W right here is constant, 100,000, whatever, okay? So you have constant value. And you have constant value of lambda, constant value of right hand side. And this is your PT, this is your QT. But Q is constant. So it's very easy to solve if you remember the equation that we just talked about. So the only thing here is this one is even this one can be solved analytically. And if I show you a simple way to deal with this, and let's say this is W prime, okay? And then we can treat this one like this, and W, and we can actually separate this like, and dt. This is 1, and so if you integrate like this, you didn't really have to use that integrating factor method, and you will have the same answer. In here we have, if you, we can just substitute this whole thing, but we can have, and then we have to apply the integration of this, and then, and I think minus sign should be there somewhere, and then T, and obviously we have C0 and CT, and 0 and T. And if you play with this, you can come up with this answer, okay? And, but the other way is that you can apply You can also apply this method and you will have the same answer. Okay? And so we had just a zero and constant, and this time we have a linear function which is like this, and this one means that you have a triple plan that the discharge rate keeps increasing because from some time, and then they start to build the next second tank, third tank, fourth tank, and fifth tank, and then they start to have produce more and more. And then in this case, I have some function which is bt, right? So we had a zero, we had a constant, now we have a linear function, and this one also is not so difficult to solve, but in this case, you may have to do something about this integration, but if you apply that method, you can come up with this answer. So if you have a W, which is this, like this, and then your concentration pattern is like that. Why are we doing this? We want to know the shape of the C curve according to that loading function. And the other way is, okay, and now I have a zero, constant, and a linear. But in here I can have some exponential function. This can be something and then going down. But in the other ways, this can go up as well, dependent on the sign of bt in here. If this is plus, it's going to go up. And if this is minus, this is going to go down. So dependent on the situation, we have the different solution. And if the exponential function is relatively easy because we had an exponential function inside that complicated integral into the right hand side. So this one is to solve. And if you wanted to know where is the maximum concentration in this case, and we can differentiate this one and put this one is equal to 0, and then we can, if we solve that for concentration, and then we can come up with this answer. So TC is representing this critical point right here, okay? And the differentiation is this one is 0 because the slope is plus and this one is minus. Between plus and minus, we should have 0, right? Good. All right. Sinusoidal is a little bit more work, but I gave you a little table, and this one can be found in mathematical and mathematical book. If you integrate this one, you can, this solution is like that. If you integrate this one, solution is like that. If you convert this one to like that. And I think you all studied this before in your high school days or in your calculus class, but this is a little bit time consuming, so you can do that. And actually you can do this by yourself by dividing this one into two different parts, and by using this principle, we differentiate is u, v, and u prime v. And if you use this principle, you can just play this around and then can come up with an answer. And anyways, we can use that form to save our time. And total solution in here says if you have a constant situation and linear situation and exponential situation and sinusoidal situation, and if you have a multiple case, this one says simply you can add them together, have a total solution. So that's what it says. And back of the envelope calculation, that's in your box, and I want you to read it over, which is in page 79. Okay? And I encourage you to read your textbook as often as possible, as many times as possible. Because Steve Jeffrey, my friend, he's a good writer, and he has a lot of intuition as well. So if you read his book, then you can develop your modeling skill, mathematical skill, writing skill, and we have a lot to learn. So back of the envelope. What is envelope? Envelope is nowadays we don't use this too often. This maybe we use it to give the money at the funeral or the wedding. But in my time, when I studied, we write a lot of letters. When I applied for school in the US, I had to send a letter, and they replied to the letter. I also sent a lot of letters to my wife, okay, to convince her that I'm the one. Yeah. But nowadays you just send the message, right, or chat or the Facebook, whatever. But we still have a lot of envelope. This is usually your electricity bill or any advertisement. So many actually envelopes were around us before, nowadays still too. And so this is any paper, any piece of paper. And that's the envelope. Back of the envelope, and when you receive the phone call, if you need to write the number, and then you just grab any paper and then write the number and throw it away and forget about it, right? And then you try to find it, and then you will find it, and you just have to call again. So that's the piece of paper that you can grab anywhere. So that means a very simple calculation. So, and he says this one is a quick estimate, but what this one says is the quick and dirty estimate. This is the one of the very often used expression for the simple something, and that means if you know something, you can quickly calculate and then make a decision about that. If you don't know, there is no way. You may need something more really serious or something, somebody who can help you. So that means this is the this kind of thing is a calculation. Then you can apply for the situation that you need to make decision. And if you have this kind of database or method or the previous experience, and then it's going to be a lot easier for you to make a decision at the site. That I call is the expert. Okay? Expert. The difference between novice or beginner. Difference between expert and beginner. And if you provide both of them enough time, that both of them can come to the conclusion, make the same conclusion. But expert will just solve the problem right away. Beginner or student, they may need to take more time. But timing is the issue many times. So expert, if you want to be expert, then you have to know many or some method that you can use. Obviously, you have to understand what's going on in your big picture. So this kind of method can be very useful, that you can do data taking a very simple question. So that's what he said. So I want you to read it. And the next page, actually page 80. Last night, through and thought about lecturing this to you. Fourier transform. Have you heard about it? Fourier transform? Laplace transform? But I decided not to because I have not done it yet. But what I'm trying to say is this is very useful method to solve a complicated system. And have you seen the movie Matrix or the Interstellar? Okay, that's the traveling space. Okay, in mathematical world, we have things like that. This is Fourier transform and Laplace transform. And by looking at it, it's very complicated problem. But if you just flip this chapter to another way, then this one becomes very simpler. And then you solve the problem here, and then move it over to here. That's what it is. So you just use that kind of method and make it very simple, and then find the solution and just move it to the new word. Okay, 10 minutes. In other words, that's very good. The Fourier transform, Laplace transform, those are very good methods for you to deal with complicated problems. And when I studied in chemical engineering before, and though I had a civil engineering background, I had a lot of classes that use mathematical methods, which were very impressively useful too. Okay, the closed form and open form. Closed form means you have solution. You have a CT equals something, and then in closed form, you have let's see, you have a functional CT, then you can have things like that. This is very good because when you have T, you can have the C. So to generate answers in a very efficient manner or to provide insight, this is very good. Okay. But nowadays we use computer. Okay, computer. Because we have a lot of questions and a lot of equations, a lot of input and a lot of processes inside, and then often my model is regarded as a black box. Nobody knows what's going on. That is not good. That is. And we use models, but we have to know what's going on. And if you don't know, then my recommendation is don't use it. If you don't know what's going on, if you don't know what is going to be the input, and there's no way for us to analyze or understand what is the output would be. So, and you can have they can lead to blunder or erroneous interpretation of this. So you always have to keep a very simple common sense in your mind before you go really complicated system. If you understand the simple one, then you can go ahead and make it more complicated. But if you don't know, go away. Okay? So this kind of equation is very good for you to understand what's going on. Sometimes it's just enough to know both ends maybe. And if you put t equals 0, then you have some kind of c0, right? If you have infinity, then you know this one can be infinity or the 0. So if you apply those two boundary conditions, if those make sense, maybe those can be safe to use. So and there are always the common sense that we have to apply. Okay, so that's so much. So you did it, okay? All right. And if you have questions, I can answer you. But if you don't have question, I want to go ahead and then start chapter 5. We have 20 minutes. Okay? So you all understood very well from chapter 1 to chapter 4. So let's have more fun, a little more fun with the chapter 5. If you take a look at this, chapter 5 is only about 9 slides. Okay. And now we study the big picture, some pieces of the model, and now we will have kind of something similar to our real system. And we can have lakes connected like that, or you can just assume those as a river, even though they look just look a little bit apart from each other, and we can just assume their distance is maybe 0 or a few millimeters, whatever. So this one can be applied in any system, and it is good to have good hydrodynamics model that can calculate the movement of your water this and that way. But sometimes, or many times, we do not have that kind of luck. In that case, we just have to simply use the flow rate, which is the case in here. Okay, let's say we know some flow rate Q is Q coming here, and then somehow flow can be divided this and that way, and the flowing pattern is like that. In this case, we have to know the amount of the flow flowing between those two cells. If you don't know, there's no way. Okay. So, what I'm trying to say is, it is very also difficult to know how much can be divided without having very good monitoring data. If you don't have data, you just have to guess, and that's very difficult all the time. Sometimes, if those lakes are connected together, they can exchange the material. Even flow can be go and come and go, and also due to dispersion, they can exchange the material. So, in here, if you have lake 1, lake 2, and if we know something coming in, let's say we know every data, every W, every Q, every K, and usually what we want to know is what is the concentration is going to be in here, first cell and the other cell. Okay. So let's try to develop a mass balance equation. From here, I have kept saying that this is a counting process. You have to, in your mass balance equation, what are coming in will be plus, what are going to be going out will be minus. Okay? All has the same unit, which is mass per time. Okay? Because this one, left hand side, is based on delta M over delta T, which is mass per time, which is mass per time unit. Okay, W1, that can include flow and concentration, and that often also can be if you have W1, that can be easily some flow times concentration. And since we have flow in here, we should have something coming in here. Okay? And if we assume this Q1, 2, and Q3 are the same, maybe we have if this one is Q, if this is Q as well, and I think we have another Q from principle of continuity. Okay? So we have what is coming in? W. What is going out? QC. What is going out? Again, due to reaction, This is K times C times V. If we have settling, we have a V times A times C as well. In here we do, in this case, we will assume everything is included in here. Okay, for the second box, what are coming in? This one, that. So these two are going to be plus for us, plus, plus. Right? What are we now? This and that, minus, minus. Okay? So mass coming in will be through some wastewater treatment plant, WQ, and something from the upstream flow right there. And then the flow is going to go out and then like that. So we're done. We're done. We developed our mass balance equation for both light systems. And in here, if you have steady state, that means your concentration is constant. In other words, constant for time. In other words, your dCdt is 0, right? 0, 0. And then, if this is steady state, it's very easy for us to solve this one for C1. In here, if you solve this one for C1, we can easily just collect these two and then move it to the denominator of the other side. So C1 is right there. Okay? And as you can see, in here, this one C1 is not affected by C2 because this one just give the system, give the whatever away. So nothing is coming in from C1. So in this case, we don't see any C2. But in C2, we should have a C1 because we are receiving some material from C1. So as you can see, C1, we can substitute this one to here. And then this one becomes our constant. And then if we use the same method, we can calculate easily from the C2, right? So we can see this one is function of C1. But in here, steady state, C1 still is the constant. Okay? So, no problem at all. And so 5.1, what is it? Yeah, solve it. Okay, for the cascade model, this is very, this, I think, figure, you can find this from other textbooks of other class. In other words, if you study wastewater treatment plant, I remember this in that textbook. Okay, let's say this is your reactor or river, lake, whatever. And even though they look like very long stick, if we assume this one is this whole thing is my one system which can be completely mixed, then if you remember if you remember this right here, this one is W1, I said, is can be expressed like Q1 times C1, right? Okay, then let's go back to the screen that we were. We had a Q times 0, exactly the same, right? Okay, so if you think this whole thing is your just one reactor, but they look a little bit not like that, but let's assume that one. So your concentration is same in all the places, but this is just ideal assumption. Okay, just accept it. Okay, right. Then this C1 and is going this is C1 is all the way. Your C0 is going to become C1 just in a right, in a flash moment, and then the kind of assimilation factor can be like this. Okay, but as you can see, this is long stick, and we can say, oh, maybe concentration here and there are different. I want to divide this system into two parts. Okay? Two. So one is here and the other is there. Okay? And then I will V1, dC1, dt equals Q0, C0 minus Q1, C, I think we have the same Q, K, C1, V. So we had C1 is Q plus K, V, and Q and C0, right? Okay, let's think about second, okay, this is V1, by the way. And then this is Q, for the same case, let's say we want divide my divide my volume two parts. Okay, in this second case. Then second case, I have my C1 is like that. And this one is, input for this one is QC1 and output is going to be QC2. The reaction is going to be K, C2, V2. So in this case, my C2 is going to be Q plus K, V2 and C1, right? But my C1 in this case is like that. So I can see this one and this one are the same. Okay? What I'm talking about is when I had just one reactor, I had a V1. Okay? When I have two reactors, which is half of the V1, which is V2. If I want to divide this to 3, that's going to be 1/3 of V1. And in here, for the simplicity, I assume my all V has the same volume. Okay, so I can just in this second case, if I divide the whole thing by 2, I can see I have one concentration, and then I have the other concentration. If I divide this on 4, I can have this one like that, and if I have infinity, and then you can see kind of shape of function, it'll be like that. Okay, then let me show you something like this one is the function of in here actually if you think about plug flow reactor. And we had things like this one. For a steady state, we assume this one like that, and then my round C, actually DC, dx is going to be minus kc. So in here, I have my Cx is C0 e to the minus k over Ux. Okay? So if we draw this one, and we can have this like that. I want you to compare this and that. Okay? This is space, right? We have let's say you have a 100-meter reactor. Okay? You have a 10 meter, 20 meter, 40 meter, and if you have X, if you put 10 in here, you can calculate concentration right there. If you put 50, you can calculate concentration like that. In here, this is discrete method. You have a certain number of reactor, same size reactor in the whole, in that whole system. Okay? So you can separately, or you can calculate this separately like this. And if you think you have so many different reactors, infinite number of reactors, then you have to use flow for reactor. Now, we assumed in the first place that this is completely mixed flow reactor, 1 reactor, 2 CMF, 4 CMF, and 8 CMF. And if you divide it into infinite number, that infinite number of CMF reactor is going to become my flow reactor. Okay? Why is this so? And since we are talking about something like this, right? Something QCX, X plus delta X, and for this little delta X, I have a delta V over dt will be QCX plus delta X, and I have a KC delta X. And in this case, what is coming in or going out, and then by the decay, which is exactly the same principle that we had a first one, second one, and third one. Okay, so in here, if we play with this, and we all know this one can become my flow reactor. I think I covered this, right? Do you remember? 내가 안 했나? I think I did it. Right? You will have to know how to move from here to there. It may appear in your little exam. Trouble. Okay. So, time variable, in this case, if you don't have this input, and we'll be happy. And in this case, I don't like this chapter, sorry to say, but all of a sudden we do not have W terms disappeared in here. Anyway, and if we carry this one, it's a little bit troublesome to solve the situation. And but the basic idea in here is how to just show the method general tendency, so it's not going to be good to make this one complicated. So if we assume this one is in here, if you have two systems, which is this, and this is the other, and then somehow if you, in this case, since I don't have C1, W1, and I don't see W2 either, and in this case, it's because system becomes a lot simpler, and then solve it. I'm not going to cover this one, but I want you to read this one as well. If you go back to your textbook and try to understand what he's trying to say. He's trying to give us kind of training to think about the system. And this is on page 92. Yeah. I'm not going to cover, but if you have the time variable situation like this, and you can have the behavior the first cell, the second cell, third cell, fourth cell, and end cell, and they have some pattern in their solution. And sometimes it's very interesting and may not be useful, but it's very important to know sometimes some basic flow inside the system. So I encourage you to read it over as well. Okay, and probably this one is the last one that I can cover in this class. And you already studied about this. If you have let's say you have reactor. At your concentration total is Ca0 at T equals 0. And as time goes by, your Ca is going to be Cb and Cc. So at time 0, your Cb equals 0 and Cc was 0. And maybe if we have enough time, maybe your C or the Ca is going to become Cb. And if you spend enough time, maybe everything will become to Cc. And in here, because this is reactor, when we talk about mass balance equation, QC0, QC minus K, CV is the usual way that we develop mass balance, but in here, do we have Q? We don't have Q, right? Because nothing is coming in, nothing is going out. So we have 0, 0 there. Very easy, right? And we have, you can cancel V. So my dc dt in here is just minus kc. For A, I can do that. And for B, and we see, let me just okay, we dca dt equals minus kca v. So I can have dca dt equals minus kca. For dcb dt, what is going on? And I have something converted from A, it's going to become this one is, by the way, A to B. And I can have something converted to C, from B to C. Okay? And then my dCb dt is without V, which is like this. And for C, what is input? For C, only input is from B. So B is receiving something from A, giving something to C, but for C, it only receives from something from B. So, and my V dCc dt equals simply this term with a reversed sign. So, if we cancel all the V in here, we can have this equation, and that equation. Okay? And this is very easy to solve. And if you already have practiced how to deal with, because your CA right here is going to be like that, and CA is a function of, this is power function, exponential function, right? Exponential function. So you can move this one to that, and then you can use integrating factor method, then you can easily solve this one. Once you have CB like that, CB can come to here, and solve it for CC. So CC is right there. And if you did your homework right, and if you still remember the method, this is going to be very easy. Piece of cake. Sometimes piece of cake is not too easy to eat, but anyway. So, this is it for today. Any questions?